All right. I've looked at the performance on exam 3. As is usually the case, most people's grades correlated closely with exam 1 rather than exam 2. There were a couple notable exceptions where people seem to have put in some extra work and done substantially better on exam 3, so kudos to them. That being said, if you're doing well, great. If you're struggling, well, this is no time to let up. Get the tutoring and press on. I mean, everything that we learned from here on out will build on section 3, on the section that we did for exam 3. We've got just over 2 weeks, just about 2 weeks left, and now we're going to see what the payoff is for the logical principles that we've learned. So that's where we stand. So today we're going to wrap up some last important principles from chapter 6, and we are going to give sort of a introduction to where we're going with chapter 7. All right, so here is one of the payoffs from chapter 6 that I was kind enough not to torture you with on our exam. The 7 S and I rules that we've learned work for statements of absolutely any length. The cardinal rule, and I encourage you to write this down and like highlight it, underline it, star it. The cardinal rule is this: for any statement of any complexity, the 7 S and I rules apply so long as you are working with only the outermost operator. The outermost operator is the logical operator that is only within one set of parentheses. If you cross into a second set of parentheses, you are not working with the outermost operator. If you cross within a second set of parentheses, you are breaking the rules of logic and your proof will not work. So the rule is you can use any of the 7 S and I rules with a statement of any complexity so long as you only work with the outermost operator. The outermost operator is the combination of the operator in the outermost set of parentheses and only one set of parentheses, and whether or not there is a negation outside the outermost parenthesis. So those are the two things you have to look for. So here, I'm going to show you how the AND rule works no matter how complicated the AND statement is. So remember, basic AND rule, from the truth of both A and B, you can infer A as well as B. Similarly, from the truth of both, if A then B, if and only if either not C or D, and if not E then F, you can break out both halves of this AND statement and get the truth of if A then B, if and only if either not C or D, and also the truth of if not E then F. But you can only use the AND. You can't reach across a second parenthesis and work with like this arrow statement. And if there was a negation outside of the outermost parenthesis, then you could only use the rule for negated and you could not use the AND rule. So the 7 rules we've taught you for S and I rules, they work with statements of any complexity, but you can only use with the outermost rule, the outermost operator. So let's look at another one. So that's and I choose and because I consider that one to be the most straightforward. So here, let's look at the false if-then, negated if-then. Remember, the basic negated if-then is you, from a negated arrow statement, you can get the truth of the left side of the statement and the opposite of the right side of the statement. So from the claim, it is not the case of if P then Q, you can get the truth of P and the falsity of Q. In the same way, you can take a super complicated negated if-then statement like if it is not the case of if both P and either T or not S, then both either Q or N and not W. You can get the match of what's on the left side of the arrow, both P and either T or not S, and the opposite, the exact opposite of what's on the right side of the arrow. You can get not both either Q or N and not W. So again, look at this complicated arrow statement, and you can see that that arrow is the outermost operator. All the other operators are within extra parentheses, but that arrow is only within the outermost parenthesis. And you have to see that there is a negation outside the outermost parenthesis. Therefore, you can use any rule for negated arrow. Someone from Oregon wants to talk to me about my car warranty. Questions? Not about my car's warranty. All right, so let's take just a little look. Let me use one of the other rules. So let's say I've got if A, then if B, then C, and I've got A. So from the combination of these two statements, remember, we have to work with the outermost operator, and that's this one, because that's the one I can get to by just crossing one parenthesis. I don't need to reach within. I can't work with this one because I'd have to reach within a second parenthesis. But from this, from if A, then if B, then C, I can get if B, then C. And similarly, if I had these two premises, if A, then if B, then C, and not if B, then C, then I could still work with this arrow and say, well, one of the arrow rules is if you have the exact opposite of what's on the right of the arrow, you can infer out the exact opposite of what's on the left side of the arrow. And this is not the case of if B, then C. It's the opposite of this. So from that, we can infer out the opposite of the left side of the arrow. Are there any of the other SRI rules you'd like to see me just do a sample with? Okay. All right, well, let's get some practice. So from the claim, it is not the case of if both A and B, then not C. What if anything can you get? All right, so we look at this. We want to work with the outermost operator, which is this arrow statement, and we have to look outside the outermost parenthesis to see if it's negated, and it is. So we can use any rule for negated arrow. And the rule for negated arrow allows us to get the match of what's on the left side of the arrow and the opposite of what's on the right side of the arrow. So because of the opposite, this not C switches to C. How many of you got that? We're getting there. Oh, let's try another one. What, if anything, can you do with this? If both A and B, then not C, and it is not the case of both A and B. All right, well, let's look at this together. The first statement, the outermost operator is an arrow. There's no negation. So we can do an inference if we have the exact match of the left or the opposite of the right. So if we have exactly affirmative A and B, then we can do an inference. But we do not have affirmative A and B. We have negated A and B, so we cannot plug that in for an inference. If we had a C, we could use that to do the other kind of inference where you have the opposite of the right to get the opposite of the left. From the second premise, we would need an A or a B to do an inference, and we also don't have those. So from this, we get nothing. Let's try another one. It is not the case of both either G or H and also either I or J. What, if anything, can you do from this statement? All right, well, let's take a look. The outermost operator is an AND, because that's the one that's only within one set of parentheses. But there's a negation outside the outermost parenthesis. So we can only use the negated AND rule. And for that, you need a second statement. And the second statement has to match one of the halves of the AND statement. Since we have no second statement that matches one of the halves, we can't do an inference. So the correct answer is nothing. If we had either G or H or I or J, then we could do an inference, and we would take the one that we have. Let's say we had G or H. If that matches half of a negated AND statement, we could get the opposite out of the remaining half. We could get a negated either I or J. All right, let's try one more. What, if anything, can you get from either both A and B, or if C, then D, and the additional premise C? All right, well, we have to work with the outermost operator. What is the outermost operator of this statement? What's the outermost operator? The or is the outermost operator. That is the only operator that's only within one set of parentheses. To use the and or the arrow, you have to cross a second set of parentheses, and that's the number one thing you're not allowed to do. So the correct answer is you can do nothing from the combination of these statements. To work with an or, you need the exact opposite of A and B. So if you had negated A and B, you could do something. Or you need the exact opposite of if C, then D. So if you had negated if C, then D, you could do something and get out the truth of the remaining half. So what some of you were probably tempted to do is get D. And if you got D, what you did is you reached within this second set of parentheses and tried to plug that C into the if C, then D. If you did that, it's a common mistake, which is why I'm warning you, don't do that. You can only work with this outermost operator, and the outermost operator is the one that's only within one set of parentheses. So if you got that D, write down in like big block letters, don't cross the second set of parentheses, only work with the outermost operator. Because you'll be tempted to do that again. And no harm, no foul. I mean, we're doing practice, which is why I'm warning you now not to do it. All right, questions about any general principles related to 613, doing the S and the I rules with longer, more complex statements. I'll also encourage you, if you know somebody that's not here, make sure they watch the video for this, because this is going to be like real important. In fact, at this point, every lecture is real important to what we're going to be learning the next lecture. So, unless they're dropping the class, make sure that they watch it and watch it closely. Yes?
I have a question not about this, but are we going to go over exam 3 at some point?
Yes, we'll go over it at some point, but nobody is yet, not everybody is yet taken. So, we're going to make sure they take it. We don't want to give them the answers just yet. All right, let's talk a little bit, sort of a prelude to 7.1. While I generally like Gensler's book, I think Gensler makes a huge mistake in the way he introduces 7.1. So I have sort of written sort of a prelude to chapter 7 to help us walk before we start trying to fly. Kind of the way I think of it. So look, in chapter 6, we've taught you the S and the I rules. But that's not where we want to end. Where we want to end is using numerous combinations of the S and I rules. We want to do what are called proofs. So the way a proof works is I give you multiple starting premises, and I tell you what I want you to attempt to prove from these starting premises. So from, given the truth of if H then not B, and if D then B, and H, I want you to prove not D. And what this will require is this will require you using a combination, a multiple step combination of S and I rules. So to get to not D, I'm going to look at 1, 2, and 3. I'm going to ask, are there any S and I rules I can use on 1, 2, and 3? Usually I encourage people to start by looking for S rules to use. There's no S rule to use with 1. There's no S rule to use with 2. There's no S rule to use with 3. You can't, there's an S rule for negated arrow, negated conditional, but there's no S rule for straight on conditional. Then I look again and ask, well, is there an inference I could do, an I rule I could do from 1? And to use an I rule from 1, I either need an exact match of the left side, I either need an H, or I need the exact opposite of the right side, which would be a B. And it turns out I do, in fact, have an H down in statement 3. So my step 4 is going to say, from the combination of if H then not B and H, I can get not B from the arrow rule from 1 and 3, also called modus ponens. So from 1, if H then not B, and 3, H, I can get not B. You all see how I did that? All right, but I'm not done. Why am I not done? Because I don't stop until I get to not D. So then I have to look again, and I have to look at statements 1, 2, 3, and now 4 to see if there's another inference I can do, another S or I rule I can do that will get me to not D, or at least closer to not D. So I look at statement 1, and there's nothing new I can do with statement 1. I already did the thing I can do with statement 1. I plugged in that H and got my not B. I look at statement 2. Statement 2 says, if D, then B. And I look at statement 4, where I got not B. So there is a rule that lets me go from statement 2, I can either match the left or use the opposite of the right to do an inference. And statement 4 is the opposite of the right. So statement 2 says, if you have a not B, you can get a not D. And I do, in fact, have a not B in statement 4. So that we add statement 5 from statements 2 and 4 using the MT arrow rule going from right to left. And then we're done, because we have proven that from the 3 given statements, you can derive a not D. How'd that go for you? I wanted to nice follow I did. And why I did that. All right, let's do another one. This time from the statements if F, then if G, then H, and if not F, then J, and it is not the case of if G, then H, I'm going to try to get a J. All right, first thing I do, I look at statements 1, 2, and 3, and it turns out from statement 1 is an arrow statement. This arrow, the first arrow is the outermost operator, So if I can either get an F or the exact opposite of if G then H, I can do an inference. And it turns out statement 3 gives us the exact opposite of if G then H. So our first step is to plug in statement 3 into statement 1 and to get a not F. We get not F from the combinations of statements 1 and 3 from the MT modus tollens arrow rule going from right to left. But we're not done, because the goal of this proof isn't to get not F, the goal is to get a J. So I glance again at statement 1. There's nothing new we can do with statement 1. We then look at statement 2, and specifically we look at the new premise that we've got. And it turns out we realize that we can use statement 2, if you have a not F, then infer a J, and statement 4, not F, that enables us to get our final J. From the combination of statements 2 and 4, the MP left to right arrow rule, and then we're done. How are we doing? You feel like you're ready to try one on your own now? Let's give you one on your own and see if you can do it. See if you can do this one. So I'm giving you 3 claims. I'm sorry, I'm giving you 4 claims. From those 4 claims, see if you can get to S. All right, who's got it? Who needs a couple more minutes? Who's utterly lost and isn't even trying? Interesting. All right. All right, so our goal here is to get to S. All right, so we look at statement one. To work with statement one, we either need a not A or we need a not F. And we have neither of those. So we can't do anything with statement one. We look at statement two. To work with statement two, we either need an A or we need a not D. We immediately notice that we conveniently have right next to it A, not D. So statement five should probably be not A from statements 2 and 3 using the MT arrow rule. All right, now that we've got not A, we have to start looking at everything again to see if the not A opens up any possibilities. And we look at statement 1, which says if you have a not A, you can get an F. We immediately notice that, hey, we just discovered not A. What a coincidence. Therefore, from statements 1 and 5, we can get an F from the arrow rule, MP minus 0. All right, but we're still not done. We still haven't found an S. We look again at 1. Nothing new we can do with 1. We look again at 2. Nothing new we can do with 2. 3 can't do anything on its own. We look at 4. 4 says if we found an F, we can get an S. And conveniently, we derived an F in our previous inference. So the combination of 4 and 6 lets us get our S by the 4 and 6 right to left, left to right arrow. How'd that go for you? Oh, good. Yes.
When I was doing it, I guess I got confused at like step 6, and I made the F negative, but because the A was negative, but since they match like 2, 5, and 1, then you don't make 6 negative. Is that how it works? Does that make sense?
Right, yes. So remember, there are actually 2 different error rules. So in step 5, so the error rules, so for step 5, the error rule says if you have the match of the left or the opposite of the right, you can do an error rule. And because you have the opposite of the right, you can get the opposite of the left. So that's why we did add the negation. But then for the next step, we were doing the other error rule that says if you can match the left, you can get the match of the right.
Okay.
So because we match the left, we take that straight on, regular F, without adding the negation. Good catch. And this is why we need to have those 7 basic rules down cold, because we're going to end up doing like 12 and 15 step proof problems. And if you do one incorrectly on step 4 or 5, it's going to make the problem impossible. Yes, sir.
On a test, are we going to be able to really answer always come out okay? Like, is it always, are we always going to be able to prove it? Or like, we have times where like, we have to break it all the
Good question. In 7.2, we will teach you a different kind of problem that you can do. For proofs, If I tell you something is a proof, that means you should be able to get this inference. And if you are not able to get this inference, you're missing something. But there is a second kind of problem I can give you called a refutation. And a refutation is where I give you several statements and I say, demonstrate that this conclusion cannot be derived from the statements I've given you. And that's the opposite of a proof. It's a refutation. So when I give you a proof, it means prove that this does in fact follow, which it always will. And the opposite is a refutation where I give you some statements and a conclusion that does not follow. And it will always be the case that that should not follow. And if you think it does, you're, again, misusing the rule. But good question. Here, let me give you a little strategy. So far, I've kind of acted as if the normal way to go about doing proofs is to just look at the statements and do whatever inferences are possible, or whatever inferences seem to get us to the conclusion. But as we get to more complicated problems, you need, frankly, a more subtle strategy. Because there's going to be times where there's lots and lots of things you could infer, but that won't actually get you to the actual end that we're trying to get. So there's something I like to call the backward strategy. And the backward strategy is simply this. You look at where you want to end up, and you work backwards. So one way to do this proof would have been to start with the conclusion and say, well, look, I want to end up by getting an F, correct? Rather, I want to end up by getting an S. So we want to ask ourselves, well, which of these four premises is at the end going to get us an S? And the answer, of course, is we're going to have to work with statement 4 to get us an S. But to get the S, we're going to need an affirmative F from somewhere. And we have to look again at the various premises and think through, well, where is that next to last inference going to be? That's going to give us the F. And it's going to be premise 1 somehow. We're going to have to use premise 1 to get us that F in the next to last statement. And then we ask ourselves, well, but what are we going to need at that point to get us the F? And you're going to need to match the match the left side of the arrow. You're going to need a not A. And then one more time, you ask yourself, well, wait a second, where am I going to get a not A from? And you look around and you realize probably by using statement 2 and by finding the opposite of the right side of the arrow, which will get you the opposite of the left side. And once you've strategized all of that out, then you realize, oh, the proof will look like this. Now, that's an advanced strategy. If you can't do all that in your head yet, that's okay. But I want you to see what these problems look like, the better you get at logic. So instead of just looking at the first 4 statements and just sort of randomly saying, oh, here's an inference I can do, maybe this will help me get closer. The more complicated the proof is, the easier it will be if you learn to work backwards rather than forwards. Because the more complicated proofs will have more inferences that you could make, and some of them won't lead you in the direction, they're not incorrect to do, but they won't move you towards the conclusion you're trying to get. Because this is how kind of the ambiguity of being a grown-up using logic, and it kind of works like this. There's lots of directions your inferences can go. Not all of them are productive directions. So there will be multiple right ways to do the proofs. There will be 4, 5, 8 right ways to do the proof. But there will be an infinite number of wrong ways to do the proof. So, and that frankly resembles the ambiguity of real life. So sometimes there's more than one right way to proceed, but just because there's multiple right ways to proceed doesn't mean that all strategies are equally valid. There's still lots of wrong ways to proceed. Questions, thoughts? Is there anything else? Oh yeah, here we go. Let me give you one more to do. Do this one. And if you can do this one, actually, you know what? 3 minutes? Yeah, try to do this one. All right, how many of you got it? How many of you are still working? Okay, I'll give you another minute. All right, well, I wish I could give you a little more time to work this one, but time's running out. So if you look at statement 2, if you have a B or the opposite of either S or R, you can do an inference. Statement 1 gives us the opposite of either S or R. So that lets us get the opposite of B. And that's from 1 to MT error rule. And then once you've got a not B, then with statement 3 says either not Q is the case or B is the case. And since this is an or, we need the opposite of one of the two sides. The not B is an opposite of B. And that gets us R not Q from 3, 4, or rule. So listen, 7.1. Give yourself a little extra time on 7.1. Don't spend more than an hour on the exercises, but give yourself maybe a half hour to actually do the reading for 7.1 and trying to grasp it. After, if you've done the reading and then tried to work the exercises for a full hour, with my permission, you can knock off after that point and be done. So give it your best shot, and we'll talk on Monday, because it's going to introduce one more wrinkle to the way we do proofs. Thank you very much. Have a good weekend. All the blessings of spring upon you. Hey, oh, yeah, sure,
Would you recommend, I can get downloads from the library, digital copy?
sure.
Would you recommend digital copy?
Are you free now?
Yeah.
Why don't you come by my office? I will show you an alternative and you can kind of look them both up and see which one you want.
I recently registered for the philosophy movies class.
Cool.
This summer. I just wanted to know what the starting date for that was.
It's June, so I think it's the first Monday in June. So yeah, I'm wrong. It's the first Tuesday in June.
Okay.
It is Tuesday, June the 1st.
Okay, thank you.
Sorry, I'm Josh.
Hey, Josh.
Nice to meet you.
Oh, yes, so you want to come
Yeah.
by my office at
3 p.m.
3 o'clock? Do you know where my office
I
is?
did not, that's why I came.
Okay. It is on the second floor of McMillan.
McMahon?
Yeah,
Okay.
259C.
I have no number. 259C?
Yeah.
Okay.
So essentially, it's on the second floor.
Mhm.
It's all the way to one side, near the philosophy and religion office.
Yeah, I think I know where it is.
Yeah, so it's got like a little alcove down the hallway. It's got like a table,
Okay.
comfy table by a couch. So
Awesome.
be there around 3. I'll be there about 3. I might be there at like 3:05. So if I'm not there right at like
I have no other
3:02.
classes today, so no rush on this part.
All right, good.
All right.
And then you can take your exam then.
All right, thank you again so much.
You're welcome. Glad to be of help.
I'm doing an independent study of Professor Kate next semester, and I'm going to focus on the semantic pragmatics of dictionary prayer.
Oh, wow, cool. Well, Tweet is quite good, especially on stuff like that.